I think we're on. I think we are on. Okay. Folks, this is where we started the other day. Yeah? Let me turn this down just a bit. So we talked about these new types of relationships. We were really good at linear relationships. Remember back in grade 9? We see that, or let me grab this thing here. We notice that these first differences are going up by 2 each and every single time. And when it does that in the first differences, we're like, oh yeah, this thing is linear because it's going up by 2 for every 1 increase of x. And we're like, yeah, we got awesome at that. It was great. Now, sometimes data will show a curve. And the relationship in a curve was that, well, it was more or less like this example over here, part B. Part A was linear for sure because the first differences are all equal. However, if you look at part B, the second differences are all equal. And some people might call the second differences the first differences of the first differences, but that's a little crazy. We got all the y values here. You see they're increasing by 3, by 5, by 7, by 9. And at that point, your grade 9 brain is telling you it is not linear. But now your grade 10 brain is going to kick in here and say, oh, well, look at the second differences. And we know that the second differences, when they are constant or when they are equal, we know that it's a quadratic relationship. Then we looked at some equations of functions. We call them functions because they could be lines, they could be curves, they could be, we just call them all functions. So in this first one here, this is a linear function because the degree on the x is 1. And also, if you look closely, it's literally in y equals mx plus b form. And we really like that form. And we know that that's a line. But when I told you, I'm like, hey, well, listen, have a look just at the degree of that function. And the degree is the highest exponent on the variable. Then we look at part B, and we say, oh, yeah, x squared. See that little square there? Well, when it's a degree 2, we know that it's quadratic. Part C didn't look quadratic until you distribute that 3x into the brackets. Notice how we have 6x squared. That's the highest exponent is the squared. So again, this thing it is, in fact, quadratic. And lastly, over here, we distributed this 2 into that. And we notice, again, it was in y equals mx plus b form. X has a degree of 1, and it was linear. Now, that's good. We look at what the graphs actually look like. And this first one feels quadratic. In fact, sometimes when I am drawing my quadratics, they do end up looking like that sometimes, unfortunately. But this one is clearly not quadratic because it's got that sharp, piercing bottom here. And it's not because they actually drew these lines incorrectly. It's not because they didn't make it actually like a smooth thing. That's not why. It's actually because this particular shape here doesn't have something called the step pattern, which we are going to get into more detail today. Or I said here, it's because it's not a smooth curve. A smooth curve looks like these guys down here. And if you notice, this is a beautiful smooth curve. And there's going to be this step pattern that exists. You will see very, very shortly. What we call these curves are parabolas, not parabolas. Okay? Okay. Then we created this massive table of values for the function y equals x squared. Yeah. Yeah. Oh, yeah. I'm ready for it. There you go. You got everything you need? Pencil, calculator, eraser? Coffee? Couple things about this. The table of values, as you might know, is the most powerful way to graph. You can graph any function of anything. You're going to see in grade 11, you get functions that look like that. You're going to get functions that look like this. And you're actually going to get functions that look like that. And it's such good stuff. And the only, well, not the only way, but a beautiful way to plot any of these functions, including what we're dealing with, quadratics, is by creating a table of values. And it's the best, honestly. So usually -3 to +3, but here we did -4 to +4, which is fine. And for every x value, we subbed it into the equation y equals x squared, every x value, and we got that y output, right? So each one of these, like 4, 16, if you go to our graph, we're going to go, okay, oh, sorry, negative 4, 16, negative 4 up to 16, and that's how we got every single coordinate on here. Notice that it creates this smooth curve. And one thing I started talking about the other day was some of the characteristics of this function, or of this quadratic. The first thing that I love is this green line. See this green vertical line? That it's literally on the y-axis. You see that? Like I said yesterday, the elementary school in us will say, oh, it's a line of symmetry. Remember that? Ramirez? Yeah, so good, so good. Now, we're in grade 10. What do we say in grade 10? Not line of symmetry. Do you remember? The axis of symmetry, yeah. And now this is going to be a little bit of a stretch. The axis of symmetry, it's a vertical line, right? And you might remember from grade 9 that the equation of a vertical line is x equals. Do you remember that? Yes, no, maybe not. Then if that's the case, then what's the equation of this vertical line, this green line of symmetry, axis of symmetry? Well, because it's right on 0, it crosses through the x-axis at 0. We'll say that this is the equation of this axis of symmetry is x equals 0. Okay? In fact, maybe I'll put a star beside that for later. The next most important thing would be the vertex here. And that's the point where the quadratic, some people might say it's like the top or maybe it's the bottom, which they're right, but really it's the point where this thing changes its direction. So if we're coming in from the left, yeah, we're coming down, 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 down. We hit the vertex, and we change direction. It begins to go up, 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 just like that. And that vertex is like, that is the one point where we start changing directions. It's great. It's important. And we're going to do a lot of work in this whole quadratic grade 10 experience on how to get that thing. Because once we have the vertex, oh, life is so good. If you have the vertex, you can graph any parabola, and you're going to come to see that. Lastly, there was this pattern that occurred. Every time we went over 1, we go up 1, over 1 up 3, over 1 up 5, over 1 up 7. And the pattern here is that we're every time we go over 1, whether it's left or right, from the vertex, each time we go over 1, we go up by the odd numbers, right? Over 1 up 1, and from this point, over 1 up 3, from this point, over 1 up 5. And that's not a coincidence. That is called the step pattern, and it's lovely. It is so, so, so good. We also talked about this frowning parabola. It's a little sad, yeah? And we also talked about, well, maybe it's sad because it's actually negative. See how it's negative x squared? And that, to be honest with you, that is the reason. What has happened is that it's the same sort of parabola as the first one, except it is, instead of facing up and smiling, this one is facing down and frowning. It has the same idea. It still has that axis of symmetry of x equals 0. That's the equation of that vertical line. It also has a similar step pattern, except each step is now negative, which makes sense because it's frowning. It's going downward. So every time we go over 1, it's like down 1, over 1, down 3, over 1, down 5. And the next one would be over 1, down 7, and then over 1, down 9, and over 1, down 11, and that will continue forever. But I think 1, 3, 5 is more than enough, believe me. The vertex is way at the top here. We actually would call this a maximum point, yeah, because it's the highest that this thing can go. And in the previous example, this vertex would be the minimum point, meaning it would be the lowest it can go. Okay. That's basically a recap of where we were at yesterday. Any questions about that? Feel all right with that? Give me something. Yeah. So, yeah, great question. The question was, what is at the top here, this y equals ax squared plus bx plus c? That is it's basically the y equals mx plus b of quadratics. It is that's called standard form of a quadratic. Now, we're going to explore each one of these letters, and to be honest with you, right now we've only explored y equals ax squared, and not even an a. Like we just had a positive, like this is really 1x squared, so positive 1x squared. Over here, this is really negative 1x squared, and there's no bx or c yet. B does something to the parabola, C does something to the parabola. Very similar to how the B value in y equals mx plus b move things around. But it's quadratic, but it's a little bit different. And honestly, not as crazy as you might think. Okay. We filled in a bunch of blanks. And this is very definition-based. Lots of new terminology. The graph is called a parabola. Yeah, we love that. And again, like we just mentioned, Boo, we're looking at y equals x squared. So whenever you see any quadratic in y equals x squared, here are the properties. Well, the graph is symmetrical about the y-axis, meaning that this axis of symmetry, which was that green vertical line, it has the equation of x equals 0. It always does for these types of quadratics. It'll always be x equals 0. The point where the parabola intersects the axis of symmetry is the vertex. Yeah. So what that's talking about is right here. The vertex is always on the axis of symmetry. It's right on it every single time. The next one here. There is a pattern in the y values. Yes. Every time you go over 1, you're either going to go up or down, depending on whether the parabola is happy or sad, by the odd numbers, which is called the step pattern, which is so good, and we're going to continue to explore that. I'm going to move this guy over here. See if you get, that's a beautiful spot. Okay, let's have a look at this bottom example here. I cut the page off with this line. It says the quadratic function to the left is represented by this equation. Here it is, Boo. Y equals negative 5x squared plus 20x plus 1. There it is. Kind of nasty. First of all, let's have a look here. It says, is the first term in the function positive or negative? So the first term, when they say first term, they're talking about the a value in that y equals ax squared plus bx plus c. This is that first term they are talking about. So is it positive or negative? Negative 5. So we'll say, yeah, this thing is negative. What do we know? I mean, we can see the parabola here. But what do we remember about when a parabola is negative? Is it smiling or is it frowning? It's frowning. And therefore, we would say, does the curve open up or down? Well, it opens downward. Does that make sense? Like, this thing is opening downward. Okay. So we say that the parabola is opening downward when it's negative. And that's not a coincidence. That is actually a property. That's for sure something that's always going to happen. If the first term, like the a value, was positive, how do you think the parabola would open? Up or down? Saying up. We say up because it's smiling, right? It's positive. Look at that. You and quadratics are more in common than you might think. Now, if you have a closer look at this parabola, we have this in standard form. So when it's negative 5, well, this is counting by some intense numbers here, but notice that this parabola has this axis of symmetry right here. Do you see it? And the equation of that vertical line would be x equals, well, it goes through 2 on the x-axis, so x, where am I going? X equals 2. Yeah? So far we know that the A value will tell us whether the parabola opens up or down. So how the parabola opens. If it's positive, it opens up, and if it's negative, it opens down. And if you have a look on the left, it says here the C value, so the ax squared plus bx plus c, this last C value is it's actually the y-intercept. Notice on this graph, this graph might not be the best graph to show you, but what I can show you is maybe some familiar stuff. What does x have to be when we're solving for the y-intercept? Remember that? If we're solving for the y-intercept, we have to set x, remember? Yeah, we got to set x equal to 0. So if you graph this quadratic, y equals negative 5 x squared plus 20 x plus 1. If we set x to 0, just like any function, you set it to 0, you're going to get a y-intercept. Well, 0 squared times negative, this is gone. And 20 times 0, that's gone. And notice how we're just left with 1. So that y-intercept would be 0, comma, 1. Okay. So we know A, yeah, smiley or frown, I don't know. C is basically the y-intercept. And I think B is a funny one. B isn't just one of those where it's like it does this or it does that. It's not truly like that. It is a funny one, and you'll see how we approach that in the next one. So this is a great page to refer to when we're just dealing with quadratics like y equals ax squared. Now, if that A value is positive, right, we know that the parabola it's positive. This thing's going to be smiling, right, because it's happy. So we know that it opens up, right? The vertex will be 0, 0, and it's also that minimum point. It's the lowest point because this thing is smiling right there. The equation for that axis of symmetry is x equals 0. Of course, it's right on the y-axis. And then the step pattern is move 1 to the right and then 1 up. 1 to the right, 3 up. 1 to the right, 5 up. Or the other side too, right? 1 to the left, 1 up. 1 to the left, 3 up. 1 to the left, 5 up. Really the step pattern here is no matter where you're going, right or left, it's going to be up or down 1, up or down 3, up or down 5, and that sort of just continues. That is the step pattern. And well, I guess for this positive one, it would be up. Now, when we're dealing with y equals ax squared, and we have a negative a value, like the a value is less than 0, yeah, this thing's going to be sad. It's going to be opening down. The vertex is still 0, 0, though. It's right there, right? But now, it doesn't produce a minimum point, because this thing is facing downward. This is actually the highest point on the parabola. So we call it a maximum point. The equation for the axis of symmetry, which is still x equals 0, because it hasn't really moved left or right. Still right on the y-axis there. And now the step pattern, the biggest difference is that, well, it's now the word down. Instead of going up, it is going down. And that's because, well, this thing is negative, right? Over 1, down 1, over 1, down 3, over 1, down 5. That's exactly what's happening here. It's now, well, I guess we could say it's negative 1, negative 3, negative 5, dot, dot, dot. Okay. Folks, there's some homework here. It looks like a crazy amount. But if you open up your textbook and have a look at it, it's really not a horrible amount. Questions about anything? Okay, good. All right, I'm gonna stop this thing over here. At least I'm gonna try to.